Right, so we're actually jumping back to a couple of pages earlier. Guys, you got that? Guys, got that? I think on my book it's 130. 130 in my book. Can we see okay?
Yes.
Yep. Now, you guys, literally like the same week we were talking about p-values and threshold values and hypothesis testing, Colin asked you, are you doing this in maths class? And he said the answer in the class wasn't exactly positive. Very much, yeah, but not with a lot of confidence, it would seem. So, yes, we are doing this in maths, you know. So, what we're having a look at today, well, later we'll need the formula book in a little bit. We're looking at something called standard normal distribution. These are usually represented by Z. Yes? It's a very special type of variable. Now, what I'm going to do as an example is I'm going to generate some random standard normal values. Let's have a look at some of them here. So let me just hang on, clear this. Clear. The heck, how do you do clear screen? I forget. Oh, there we go. Okay. Here are 10 standard normal random values. So, what can we say when we look at them at a glance? Roughly speaking, what does their average look like it could be? Yeah, something you would say close to 0, right? I'm just like, you can't quite tell just accurately, but just from a rough look at it. Let's generate some more. Let's say there's 100 values. The average, no, I'd say it's going to be 0. Now look, I can calculate it for you, okay? There's 1,000 values. Let me just save the 1,000 values. Data. Okay, yeah? Oh yeah, that's way too hard to see, isn't it? Because it's black. Okay. There's 1,000 values. Let me get the average here of them. Nearly 0. Now, the thing is, if I generate a different 1,000, I get a slightly different average. What about if I generate 1,000,000? 1, 2, 3, 1, 2, 3. Hopefully this won't crash the computer. Oh, processing. There we go. So, what do you think the true average is if you made your sample big enough?
0.
Probably 0. Okay. I think I can also get the standard deviation. I think. Can't remember how to. No, what is it? Actually, you know what I can do? I can do this. There we go. No, that's not it. Well, there's the average. Where's standard deviation? No, I can't remember the function. Anyways, I'll tell you. The standard deviation is 1 and the mean is 0. So what's one fact about this is it has a mean of 1 and a standard deviation oh sorry, a mean of 0 and a standard deviation of 1. I've crashed that now. There we go. Oh, maybe this is it. Stir? No, I'll have to look it up. Okay, so why is this an important random variable? Well, it's important because later we'll see it's going to be used as a basis for something else. But right now we can just imagine z as being just a random variable. On average it's 0 and its values tend to be near 0. If you were to look at some, let me just get some values here. Let's make 100 of them. What looks like the biggest value? Can you see most of the, not many, but some of the values are in the 2 range. Can you see that? Yeah, but most of the time it's in the 0 or 1 range here. So you might ask a question like this. What is the probability that our z value will be bigger than 2? Now, I can get a rough idea from this sample here. How many of these numbers were bigger than 2, for example? 1.
2.
Now, these are minus 2s. So, 1.
Just 2.
You just see 2 of them? 2.
3.
Middle?
Come on,
Oh, here, right. Just 2 away from it. 3. So we think if you were to pick a random number like this, about 3% of the time it would be bigger than 2. Now, of course, we need a precise way to calculate this, and there is a way to calculate this using the table book here. What can we do here? There's a special type of curve called the standard normal curve. And you've actually seen a shape like this before. It's a little bit like a bell curve. Here is 0. This axis here is the z-axis. Here is roughly 1 and here is roughly 2. Here is roughly -1, here is roughly -2. And if you want to answer a question like what is the probability, for example, that z maybe is less than, let's say, 1, for example. What you do is you mark off 1 here and all the area to the left, because you're looking at less than. Whatever this area is actually the probability. Now, what's really nice is this has been calculated in the table book for you. The symbol, I think, is this symbol. You look up the table book for value 1, and it tells you the area to the left. Now, I can open the formula book here, but while I'm doing that, you should open up the formula book. I have to get internet. I can't. You're looking for a table called standard normal or normal distribution. Page 9. Okay. Load in. Come on. Right, here we go. Right, here we go. I'll show you how to use this formula book now. Maths for Science. Okay. Where's the formula book? Here we go. What page did you say? 9? Yeah, okay. Right, what you do you just go down to value 1, and you see that you get 0.8413. Now I'll explain these other ones in a moment. So the probability that z will be less than 1 is equal to, in this case, 84%. Now let's have a look at my data here. Oh, where's my data gone? Here it is. Would you say roughly 84% of these numbers are smaller than 1? I don't think so. I can actually tell you exactly how many are smaller. 80. Okay, so that's not bad. Now suppose I was to ask you a similar question. I said, what is the probability that you will be more than 1? 1 minus this, isn't it? So what's that? 15.87, is it?
Yeah.
Okay. Now, you might be wondering, what are these extra ones for? This is when you have 2 decimal places. So for example, I might ask you, what's the probability z would be less than 1.23? So what you do is you go down to 1, oh not 1.2, sorry, see there? And then you need to go across to 0.03. So this number here is 1.23. It's 0.8907. Now before I continue, I'll just give you one to practice. I want you to tell me the probability z will be more than 0.51. So using the table book, tell me what you get here. And just remember, this is a more than. And this table book is only for, it doesn't say it here, but it's only for less than, yeah. This should remind us of another table in the formula book, doesn't it? Yeah, less than is common. You got that? 0. So it's going to be 1 minus, and then if I look here, 0.51, 0.51 is this one here, 0.6950. So what's that? 0.305? Yep. About 31%. Now, we have a very small problem, but I can show you how to fix that. Suppose I ask you, what's the probability that z is smaller than minus 1? Well, let's go back to our data here as an example. And let's check actually what that would be. About 16 in the 100 is less than minus 1. So I'm expecting an answer of about 16%. So we would have to go to our table book, and remember this symbol here means to look up in our table book, the value of minus 1. And we discover straight away the problem. There is no minus numbers. The first value is 0. But there is a simple way, a very simple way to fix that. Yeah, it's to do with the fact that this picture here is it's a symmetric picture. So if I was to ask you for something like the value at minus z, okay, that would equal the same as 1 minus the value at z. Now let me explain why. Here is z, here is the value at z, and then 1 minus the value at z would be this value here. And that's the same as that. So basically you can use this rule here to help you with negative numbers. This would equal 1 minus, and you look up the value of positive 1. Now we know what this one is already. Positive 1 we said was, did I not write it down? Oh, there it is, yeah. 0.8413. So this one here would be 0.1587. Pretty good, since I thought the answer would be about 16%. So all I'm doing right now is just using the table book to look up values here. Okay. Let me give you one to try. Oh, sorry. Is that okay?
Yeah.
I'll let you try this one for me. What is the probability that Z will be bigger than minus 1.53? And before you do it, let's get a rough answer here. Roughly, the answer should be about 95%, somewhere near this. So, see what you can get for this one. Okay. Right, first thing first, what's wrong with this? And negative, and it's a more than. So let's deal with the more than first. This will equal 1 minus the probability that Z is less than minus 1.53. Good. Which means we should do 1 minus, and then we look up the value of minus 1.53 in the formula book. However, can we look up negative values? No, but if we use this formula here, we can change this into 1 minus bracket 1 minus 1.53. But this is nice, because what happens here? The ones cancel, and we end up just having to look up the value of 1.53. You have it, do you? 1.53 is 9370. 93.7%. 93.7% of the time will be more than minus 1.53. Okay, I'm going to do a harder one now. I want to see if you can figure it out before I show you. Suppose I ask you, what is the probability that Z will be a number between minus 1 and 2? And before you calculate, let's get a rough idea of what that is. Data needs to be more than that, and the data, more than minus 1, and, hope this works, less than 2, and less than 2. Oh man. How do I do this? Wait. I don't know. I don't know how to do it. Right. See if you can calculate it. Might help if you picture it too. 0, minus 1, 2, and you're looking for this area. I give you a little hint. It's better to start thinking about from the 2. And then think about from the minus 1. The heck? What you got? Could be. So look, this area here will be between minus 1 and 2. So what you could do is you could get the area to the left of 2, but then you would have to minus the area to the left of minus 1. If you got all this area, and then you take away this area, you'll be left with what you want, which is this area here. Small problem. This is okay, but this is not okay. So we'll change that to 1 minus table 1. What happens here? Well, nothing really, except this minus and minus becomes a plus. So it'll be this plus this minus 1. So let me go to the table book. It will be 0.8413 plus 0.9772. This one here? Because of this one, minus 1. Yeah? What's this equal to? So about 82% roughly of numbers will be between minus 1 and 2. Question? Yeah?
What's the rule of changing minus 1 to 1 minus table?
Yeah.
1?
Yeah.
What's the rule?
Oh, that's just the rule I mentioned earlier for dealing with negatives, this one. That's all.
Alright.
It's nothing really to it. Now the reason we're doing this is because we'll discover in the next lesson this morning that this Z here, it might seem a bit strange. Like the Z doesn't represent anything. It's not like where's it gone? It's not like these represent something in nature, do they? It's not like, oh, these are the, I don't know, heights of people or the whatever pH levels or something. They're just these special, they're just special random numbers. But what we'll discover in the next lesson is these special random numbers here can actually form a basis of many, many types of random numbers in nature. Okay, so forms a basis later of many random values in nature. We can't see it right now, but very soon this morning we'll see that this Z is actually it's like a feature of biology, nearly, not just biology, but we'll discover that a lot of things in nature have behind them this Z value. Okay? I'm trying to think of an example that you would appreciate. No, yeah, I was trying to think of a non-cheesy example. No, yeah. It's kind of something like this. Yeah, but that's too cheesy as an example for me. The only examples I can think of are examples in physics, which won't mean much to this class. So, well, we might have talked a little bit about this in biology, like kinetic energy. A little bit, maybe. So, like, you discover a lot of things in science comes back to conservation of energy. You know, energy just gets transferred from one part of the system to the other part. You know, so energy is kind of like a basic structure behind most mechanisms. You know, like even if you take something like photosynthesis, have you done this? Yeah. So the energy comes in the form of a light photon, and then it strikes the inside of the cell and causes a vibration, and this vibration releases an electron, and this electron has kinetic energy. So the whole process just comes back to, well, energy gets transferred from the sun to the vibration and frees an electron and so on. You know, that's what I'm trying to say here. A lot of data that we see in nature has behind it this Z concept. Okay. Now, I'll let you try these for a few minutes, but I don't want to give this too much time, because what's much more important will be the next lesson where we make the connection. So, Oh, before I do, I just need to give you some symbols. This symbol here is a Greek symbol. Does anyone know its name? Just throw it out there. No. Does anyone know its name? Mu. And it means mean. And for this one here, the mean is 0. And this symbol, I hope you know, this one here is sigma. And what does it mean? It means standard deviation. And for these problems, its value is 1. Okay. So what I want you to try now is just questions, let's see, 5 to 10. Should only take you a few minutes. Yeah, 5 to 10, and not 5, 2, and 10. Okay.
Can you please zoom out so I can see the whole horizon?
How far?
Yes, thank you.
It's going to be on YouTube, you know. What are you trying to get? Yeah.
Sir,
Yeah.
the table in
Yeah.
is for 100 that are there.
No, technically speaking, it's for infinite. If you could somehow make an infinite sample. So they're all probabilities. So what I was trying to show you, Carul, is I could get a rough answer by generating 100. But if I was to generate, say, 1,000 and use the 1,000, like, let's take the last one let's take one we did earlier. Where's it gone? The probability Z is less than 1, we said is 84.3. So what I'll do is I'll generate, how many do you want? 1 million? Why not?
Yeah.
Okay, and let's see, how many did I say would be more than, or less than 1? 84.3. I got 84,059. That's pretty close to 84. Yeah. So what do you think if I generate 10 more, 10 times more? Takes longer. 8412. So technically, if I went infinite sample size, I'd get the precise answer. Will we do one more level? Steady. Computing. 10 million. 84,129, which we would round off to 84.13, which matches precisely now the value here. Yeah. Okay, well, can I close this?